about during the last few months is about trying to understand the deformed Amplituhedron at 3 loops. So as you are presented, we have a result at 1 loop, we have a result at 2 loops. Then what happens at 3 loops? Do we have some fancy new behavior that appears? And what can we say about that? This is still work in progress. Most of our understanding is really archaic for the moment. It's not very concrete. We have some method in order to kind of bootstrap the canonical form in this space, but I will try to give you a first glance at this kind of computation, and maybe after that we'll have useful discussion, maybe with somebody related to these new kind of exotic objects. So I will try to be fast on this part. As you are presented, we start from the 4.mhv Amplituhedron at L loops. We have a configuration of external data in twistor space that bounds our loop momenta, and they also verify mutual positivity conditions. By the fact that we work in twistor space, we should expect that the canonical form that we derive from this space should be kind of like dual conformal invariant, in the sense that if we rescale our external kinematics or our loop momenta, we should expect the form to be invariant. This will be the first main point of how to bootstrap the form, and I will try to explain in more details what will be the procedure. So on this place, we introduce this deformation parameter that I call rho and eta, rho tilde and eta tilde. That defines our deformed Amplituhedron. We deform only the external legs. The mutual positive conditions between the loops stays the same. And in order to introduce these parameters, they need to carry conformal weights. So if I imagine that I formulate an ansatz for my canonical form on this space, so that we have like the most general dual conformal invariant ansatz, well, by introducing these deformation parameters, we are kind of adding new terms that can appear in our bootstrap here. And so this will lead to a lot of complexity in trying to fully fix all the coefficients in our bootstrap, and that's the main difficulty we encounter in really fixing the form from this ansatz. So here are the steps of the strategies we are trying to follow. We formulate an ansatz with the most general numerator we can think of for the canonical form. The boundary structure in the denominator, we know it. We know it will be formed by these mutual positivity conditions between the loops, as well as the external kinematics positivity condition on the loops. And from this ansatz, we will try to understand the which term contributes to this geometry. Some of them won't be allowed because we'll take some cuts and we'll realize that we are taking a residue outside of the geometry we're looking at. This is really related to what, for instance, Yaris presented yesterday with these residual arrangements where, well, you try to find the adjoint in order to cancel the poles that are outside of our geometry. Here it's a more practical way of doing it. We will do this general ansatz and try to remove all the contribution that will give residues outside of our geometry. And at the end, this really general approach will also input some non-logarithmic contribution that we should get rid of by doing this kind of technology. So first let me present quickly the 1 and 2 loop geometry that Yara already presented, but I will try to mention one important aspect that comes up at 1 and 2 loop. The idea is that what we see is that the form stays planar. Well, at 1 loop, this is kind of trivial, like conformal, the dual conformal symmetry imposes that the numerator is 1 up to kinetical coefficients. And so, well, bootstrapping this example is very trivial. It's instantaneous. We get just the usual 4 boundaries coming from the kinematical data. At 2 loops, if you do the same exercise, there are additional terms that I did not write here, but these additional terms that appear now in this context corresponds to non-planar configuration that we manage to exclude by doing certain cuts that violate certain inequalities and corresponds to residues we don't want and don't describe our geometry. So at the end, the 2 loop geometry can be expanded in these 2 box diagrams. where the way you interpret these diagrams are the following. Each box corresponds to one diagram, and each line adjacent to each momentum is associated to the corresponding boundary. For instance, this one will be AB12 hat, this one will be AB12 hat, this one will be AB123 hat, this one will be AB1, AB2. So only a certain class of terms will respect this polarity structure, and we manage at 2 loops to exclude the ones that are non-planar. But then what happens at 3 loops? Well, we start from the most general ansatz we can think of. We formulate a numerator, and then we fix our denominator by respecting the boundary structure we expect from the 3 loops. That is, we have 3 loop lines in twistor space that have a mutual positivity condition, and then we have the usual 4 boundaries coming from the kinemical data. Now, if we want to fix the numerator, the most general term that can appear is a term of this form when you have a product of 6 determinant of either the thick lines or this 1, 3, and 2, 4, and 2 of them are for each of the loops. If you try to do the combinatorics of how many terms can appear in the syntax, you'll find that there are like hundreds of terms that can appear in this context, and so this is a huge ansatz that we will try to fix by doing this strategy I described before. So, the main problem we find with this strategy is being systematic. In some way, when we try to isolate some contribution of this numerator, well, taking the residue becomes very hard. Well, becomes harder, or at least non-systematic, because like the geometry becomes kind of non-linear on this case. If I could, for instance, ABZ1, well, all this external data, and I look at the mutual positivity condition, I end up on quadratics that are quadratics in each variables that are defining the remaining induced geometry on this residue. And then what we want to do is see if the term corresponding to this cut is allowed or not in our numerator, and we need to cut further this mutual positivity condition. So we are doing some residues of quadratic equations in this space. This is kind of, at least for me, this is not I don't have a systematic way of doing it for a general case. But for instance, if you had like a set of linear inequalities, well, we can just solve the linear equalities and just get a solution. Here, with some quadratic equation, well, you need to find some kind of parameterization to make the boundary trivial, and then on this cut, you find the induced geometry along this boundary. If I try to do this exercise on specific terms on my ansatz, well, I can do it. This is like on each particular case, this is not that hard, but in order to fix everything, we have hundreds of terms that appears, and most of them were not, for the moment, explored. But we have some expectation of what happens with this procedure. Most of these terms correspond to non-planar contributions, and as we saw in the 1 loop and 2 loop cases, only planar ones will appear. In the 3 loop case, when we do this procedure and we try to isolate each of these terms of this residue procedure, we can exclude most of them all the ones that we already tested. And we believe that if we do this procedure completely, all the terms corresponding to non-planar contribution will disappear, and everything will collapse to only planar contributions. One thing we managed to prove is that the planar configuration that are inherited from the deformed Amplituhedron stays logarithmic in the sense that we can reach a leading singularity. Now, how do we really write them as the log form is another problem. Along the way, we find some, as I said, some quadratic equations, some coordinate equation, and it's non-obvious to us for the moment on how we write precisely, for instance, the tennis court as a G-log form. But we can reach a leading singularity, which was not obvious for us initially, where initially we were expecting that maybe by removing some of the cuts with this deformed parameter, maybe we would reach some elliptic cuts where we have like some square root of a coordinate that appeared in your in this tennis court. Along the way, also, if you consider all the planar contributions, well, compared to the undeformed amplituhedron, we also have what we call contact terms, which are the tennis court where we remove some of the boundaries. These contact terms are new in the sense that they are not appearing in the undeformed amplituhedron and are kind of proportional to the deformation parameter. Well, if we assume planarity, we can exclude these contribution also. They do not contribute logarithmically to the form. Basically, this one has a double pole, and these two, if we look at the geometry and try to take the residues and see what is the contribution of this one, we'll see that along the way they will violate some inequalities of our geometry. So let me conclude on this. Mainly what we think now to do this procedure fully is a more systematic approach of considering these nonlinear geometries defined by these quadratic inequalities when you take these residues. As I said, the expectation at the end is that the three-loop amplituhedron can be expanded as the usual undeformed amplituhedron diagram structure, but now we have just deformed external data. And I just wanted to mention also, as Joris did it, the Brown-Dupont paper that has a first step along this understanding this new kind of positive geometry that are defined through polynomial equations. That maybe this would be a path we can follow to try to better understand how these hidden nonlinear geometries in the deformed amplituhedron can be understood in more details and maybe find a more systematic approach to understand the deformed amplituhedron. So that's all I wanted to say. Thank you for your attention.
Thank you for the very nice talk. Some questions?
Sorry, can I ask a question? Yeah, so at three loops, I think maybe Yara showed some things and you talked about three loops as well, but how explicit are the integrated answers in terms of polylogarithmic functions or so on that you can extract from the pieces that you can integrate?
This is for one something we did not explore, integrating this form.
I don't think there's no explicit answer at three loops?
No.
Even for these sort of pieces of the negative geometry that you have, or is it just, I don't know, so you talked about different things, I guess, but there are these pieces of the negative geometry and there's this deformed thing. But
the free-loop Wilson loop was calculated.
Right.
Yeah.
4 points.
4 points.
Yeah, okay.
Yeah.
But with this deformation?
No, because these are basically, well, we are doing something in deformed amplituhedron that hasn't been explored at all, but there are these Coulomb branch amplitudes.
Yes.
That there is an intersection with that. Yeah. Now, the Coulomb branch amplitudes which come from this deformed case are a little different than the Coulomb branch that most people studied before. It's not the algae and it's not that what they study from ADS.
Not quite the same functions as these.
Yeah, they satisfy different mass relations. Okay. Yeah. So they seem to be simpler in this regulator case. So it much quickly reveals the cusp anomalous dimension. It's simpler functions, but it's a different mass configuration that was studied in the ADS space. Yeah.
So two loops between the two ladders, there is an unconstrained coefficient, right?
Oh, you mean between this coefficient and this one?
Yes.
This is true in the undeformed case. In the deformed case, this is not the case. We have less cuts we can take, and so usually the cut that we could have taken in the undeformed case is not available anymore. And so now we have free coefficients that in general can depend on our deformation parameters.
Right.
And for the moment, this is also one aspect that we want to explore is how can we get this numbers like this coefficient from the geometry, maybe defining a geometry in higher space with the deformation parameters included in it.
I wanted to ask if you know the number of unconstrained coefficients at three loops.
Do you mean how many terms do we have? Mm-hmm. Well, if we expect to have precisely the triple boxes and
But do you? Or?
So basically, each diagram has its own coefficient.
yeah.
And you have nothing more than the planar diagram.
Yeah. So this is actually, you're asking a very interesting question. In the undeformed case, the individual diagrams at any loop order have unphysical singularities which cancel. So if you basically started with the expansion in terms of diagrams and only impose cancelling unphysical singularities, you would fix everything up to an overall constant. Here, in the deformed case, it's different. Each diagram has only physical singularities. There are no unphysical, because always the unphysical comes from these collinear regions and so on, and they are exactly not here. Yeah. So now the thing is that if you want to relate the diagrams together, you would have to add the deformation parameters in the geometry, which we haven't done here. Here the deformation parameters are external parameters, but you would have to add them to the geometry, and then there would be some enhanced dual conformal symmetry, which also has these deformation parameters. Well, I don't know yet. I don't know how to do that. Yeah. So there would be some higher form of symmetry beyond the dual conformal.
But purely geometrically, like the space of logarithmic forms is like one-dimensional at two loops. One could say that, right?
Yeah.
Because up to an overall factor,
Yes.
you have 1 degree of freedom.
Yeah.
But do you have an understanding of how many degrees of freedom are there at two loops?
It will be all diagrams in the
Yeah, all planar diagrams.
But nothing more. That's also
well,
something to compute it, or?
that's the thing which must be finished, yeah, because you have potentially these other things,
So
and you have to exclude them. Yeah. Well, the fact that the planarity stays, it's surprising, yeah, because the planarity is a very subtle. What is planarity? There is no definition of planarity other than expanding the thing in terms of planar diagrams. And it was a very subtle consequence of these positivity conditions for the amplituhedron. Yeah. For example, these negative geometries are not planar exactly because you just changed some inequalities. Here we are changing inequalities, but it seems that we are changing them in a way which keeps the planarity. Yeah. Of course, if you want to make any connection to Coulomb branch amplitudes, the things need to be planar because the Coulomb branch amplitudes are planar. Yeah.
And if you know the question, maybe let's send the speaker again.